So the basic idea is that if I have a, so in my 3-year 0, here's time 0, time 1, time 2, time 3, I have interest rates on my lattice, or I have prices. And so if I wanted to use the 1-year prices, the interest rates, let's just do one calculation. So if I put $1, this is now for a 3-year. It's a recombining lattice, so it's a little bit simpler than we had before. And so I have, let's call this R, let's call this R, D, R, U, R, U, U, R, U, D, R, D, D. So what we can do is, let's calculate 1 to show the procedure. So 1 is either equal to, it's an expected present value. So I take $1 times 1 plus RUU to the minus 1 times P, which is a half, plus 1 times 1 plus RUD to the minus 1 times 1 minus P, which is also a half. I could have, in fact, used the prices. I could say that this is, in fact, the price of a 0. So let's just keep it this way. 2 is the same calculation using RUD and RDD. And then I can get 3 from RU and RD. 3 comes from, I have to use the 1 value with the upper interest rate, 1 plus RU to the minus 1 times a half. And then I'm going to use the down value, 2, with the down interest rate and the down probability, which is also a half. And finally, once I get the 3, I get the 4 by present valuing with R. So the procedures here, although they can look different, it's worth spending a little bit of time to realize that these are just different ways of implementing the same calculation, that we're always in these zero coupon bonds working our way through the lattice the same way, and it's just a question of where we start. Sometimes, and what the book did in pricing the 3-year lattice was it started with number 1 and 2 that came from the calculated lattice of 1-year bond prices. It had already gone through the first step, so it didn't need to do it. And it started with 1 and 2, and then it just produced 3 and 4. And that's the difference. Verifying volatilities require us to look at the forward value of a 0. So, for example, what I need to do is to look at the 2-year zero coupon bond at time 0 and look at the 2 prices of that bond at time 1. There's an up price and a down price. I then need to convert those 2 prices to yields and use the yield formula. The yield volatility formula is a half the log of the ratio of yields. I get the ratio of yields by inverting the prices and subtracting 1. And we see that for the 2-year bond, when I look at the prices in 1 year, I get a 10% volatility from the table. If I look at the 3-year bond, again, there's 2 prices in 1 year time. There's the up and the down. And we can then get, from that, 2 prices. We have to use a negative half exponent because it's a 2-year annual rate. And we convert it to a yield in the usual way, and we get a 15% fall. The way we construct these lattices in the first place is basically reversing the calculations we just did. We just did a series of calculations that allowed us to verify how a given lattice can be confirmed to have the properties desired in a table. If we implement identically those same calculations, keeping in them unknowns, the RH and the sigmas as unknowns, and equating them to the characteristics from the original table, that then allows us to solve for those unknowns. And that's what's done here. So the first one's an obvious one. The 1-year rate is 10%. And so we obviously know the 1-year bond price from the 1-year rate. So that's a given. Now, let's say that we want a 2-year bond price to be correct. We have a 2-year bond yield, so the price of the 0 is 81. That's given from the table. We know the 2-year spot rate. We can calculate the 2-year 0 coupon bond price. Now, if we just say, well, how would we have calculated if we had the general notation from our Black-Derman-Toy table? How would we calculate that price? Well, we would have a discount. This goes from time 0 to time 1. This is the present value. And then in this, you see an expected, with the risk-neutral probability, an expected value of 1-year 0 prices. Each one of those is given in terms of the 2 interest rates. So here we have 1 equation and 2 unknowns, R1 and sigma 1. We clearly cannot solve it. However, we also have a requirement for the forward volatility, namely that the 2-year 0 coupon bond, its yield in 1 year will be the 2 1-year spot rates. And so we have an equation here, and this equation reduces quite easily, and we solve for sigma 10%, and then we get the R1 of 10.82. And so numerically, we just continue to proceed in this way, and obviously it gets numerically more cumbersome to do, but one can certainly use a variety of numerical software to estimate these parameters. Finally, the price caplets and caps, or the price, the option on the 0 coupon bond as in the black model. We already discussed that in the prior module for a general binomial lattice. It would be no different here. We would calculate the terminal values of the caplet, or the terminal values of the call on the 0 coupon bond, and using the standard backward substitution calculation, move our way back through the lattice to time 0. If we had a cap whereby not only did we have at the terminal point payoffs, we had payoffs at other nodes, we would simply remember that every time we do a backward substitution from one node of payoffs to the next, we need to add the payoffs at that node. And then we can accumulate the total value of a cap all in one sweep through the lattice rather than have to price each caplet separately.